Problem 3.1-1. The problem reads, the brass rod with a modulus of elasticity of 101 gigapascals is subjected to a force of 100 kilonewtons. The diameter of the rod tapers gradually from 100 millimeters at A to 50 millimeters at B. Determine the deflection at point B relative to point A. Here is the structure. It's fixed at A. B is free. Here's the end of the force at B. It's 2 meters long. We have everything we need to do this problem. The first thing I'm going to do is find the cross-sectional areas at ends A and B. Now we have the areas at both ends A and B. And the problem statement said that the cross-sectional area tapers gradually between the two ends. We can assume that means that it is a linear change in the cross-sectional area between ends A and B. What we need to do is come up with an expression for the cross-section in terms of a variable we'll call x, and we'll define x as being 0 at point A and 2 meters at point B. This is a common expression for the equation of a line. You can see the line has a slope times the variable x plus b is the y-intercept. We want to write an equation for area. There's going to be a linear equation. It will have a slope term in it, multiplied by x, and also a y-intercept term. Based on the way we've defined x, when x equals 0, our equation for cross-sectional area must give us a value of 0.00785. That's the area we computed at point A. We can set that value equal to the equation m times x equals 0 plus b. Solving for b, we get b is equal to the cross-sectional area at A. We also know that when x is equal to 2 meters, our cross-sectional area expression should give us a result of 0.00196. That's the area we found at B. We can set that area equal to our expression, which is m, the slope, times x is equal to 2 meters, plus b, which we found to be 0.00785 meters squared in the previous step. And we can solve for m. And we get m is equal to negative 0.00295 meters squared per meter. Now we can write our expression for cross-sectional area in terms of x. Here's our expression for the cross-sectional area at any point x in the member. I've drawn a free body diagram of the member. With 100 kilonewton force applied at point B, the reaction at A must also be equal to 100 kilonewtons. That means the internal force throughout this member is constant at 100 kilonewtons, and it is in tension. We can now calculate the deflection in the member. It's going to be equal to the integral from 0 to L of the internal force P divided by E and A. For P, I've substituted in the value of the internal force, 100,000 newtons. E, we were given the value for modulus of elasticity as 101 gigapascals. That's 101 times 10 to the 9th newtons per meter squared. And the term for area is this equation that we derived above. In this step, I have simplified slightly our integral, and now I am ready to do the integration. I integrated the expression, and now I evaluate it from 0 to 2 meters. That gives me a deflection of 0.466 times 10 to the negative third meters, which is 0.47 millimeters. And the problem is done.